Alright, nerds, so here we are to talk about acids, and in particular, today we start on our environmental aspects of acids, like how when acids enter our environment they can cause problems. And we'll allude to one of those today. So basically, the dot points today are to identify oxides of nonmetals um, as acids, and to be honest, metals as bases. And we also want to analyze the position. So, how does their position of the periodic table affect the acidity or basicity of their oxides? All right, so what's the point? Basically, by the end of this, you want to be able to identify and explain the acidity and basicity of oxides. You want to define the term amphoteric, and you want to be able to predict whether an oxide is going to be basic or acidic based on its position in the periodic table. You should also be able to explain that prediction. Things you need to remember from previous lessons. Group 8 elements are inert, don't form oxides. We don't need to worry about those anymore. Well, for this topic. Um, Acids in water create hydrogen ions or hydronium ions. When we say or, it is not an either or, it is depending on how you draw it. So if you draw it as hydrochloric acid is aqueous, it becomes hydrogen plus Cl, or hydrogen ion plus a chlorine ion. If you draw it as hydrochloric acid plus water, it then goes to chlorine ion and hydronium ion. You'll see that the charge remains the same. That should be a lower 3 down here. The charge remains the same. The particles are conserved. There's no real drama either way. So, bases in water create hydroxide ions. They neutralize with an acid to form salt and water. So that's what a base is. That's what an acid is. Neutralization is an acid plus base goes to salt and water. And essentially, oxides are any chemical compounds which are formed when an element reacts with oxygen. Okay, so let's get into the new stuff. Over here we see magnesium burning in oxygen, and that's where we get magnesium oxide, and that'll be relevant in a second. So metals tend to form basic oxides. So these are oxides of metals act as bases. How is that possible? We'll see that in a second. Well, basically, with water they react, so they react with water to form a hydroxide, and this makes them basic, or makes them act as bases. So magnesium oxide, we dissolve that in water, and what we end up with is magnesium hydroxide. And of course, if we were to break that down into its ions, we get magnesium ions plus 2 hydroxide ions. Oh, it should be OH. My bad. You get the point. They turn litmus blue. So if you dissolve a magnesium oxide, so if you dissolve a metal oxide, magnesium oxide, into water, it needs to be moist, it will turn litmus blue. They neutralize acids. Okay, so if we put magnesium oxide into an acidic solution, it will neutralize it. So they neutralize acids to form a salt and a water. For example, magnesium oxide, if we add it to hydrochloric acid, we'll get water plus magnesium chloride. Cool. All right, acidic oxides. So metal oxides are basic, non-metal oxides are acidic. And we see this down here. This has not been the hugest problem in your lifetime, but just a generation previous, acid rain was essentially happening across the globe because sulfur was being pumped from factories and burning of coal into the atmosphere. Okay, so nonmetals tend to form acidic oxides. In other words, oxides of nonmetals act as acids. So when they're dissolved in water, and that's why, so it's this dissolved in water stuff, that's the important part. So indicator paper must be moist to measure the pH of solid oxides. Alright, they react with water to form hydrogen ions, or they then form an acid which will form hydronium ions. So here we go from sulfur dioxide, dissolve it with water, so it's the gas dissolving into a liquid, and we end up with sulfurous acid. So it's not sulfuric, it is sulfurous acid. Sulfuric has a 4 there, 4 oxygens. This is sulfurous acid. So, as we were saying earlier, if we put sulfurous acid into water, these are the ions we get. Okay, so it turns litmus red, and that's your hydronium ion right there. They neutralize bases to form a salt and a water, so they are acids. And here's the next one. So if we add sulfur dioxide to sodium hydroxide, we get water plus sodium hydrogen sulfide. Cool. All right. So an amphoteric oxide. What does this mean? Well, basically, amphoteric means it can exhibit both acidic and basic properties, and an amphoteric oxide can exhibit both basic and acidic properties. But what it means in our context is that they react with strong acids and strong bases. Okay, so they will neutralize both. Aluminium oxide is a really good example, and we'll get to where that is in the periodic table in a minute. So aluminium oxide, if we put it with hydrochloric acid, which is a strong acid, it will neutralize the same way a regular basic would. Aluminium oxide as a acidic oxide. Aluminium oxide as a basic oxide. I've got this backwards. That should be basic, because here it's neutralizing an acid, and this one should be acidic, because it's neutralizing a base. So aluminium oxide as an acidic oxide will neutralize a base, a strong base, as we discussed earlier. Alright, so the periodic table, how does this relate? Basically, in our diagram here, and this is just from your textbooks, you can see that the metals generally form basic oxides, the non-metals generally form acidic oxides, and in the middle here we've got these amphoteric ones. Now these aren't all quite amphoteric, it depends on the oxidation state, but generally this is where all our amphoteric ones live. I'll just quickly, some of them can be neutral as well, like it can be either or. So the trend is from basic to acidic across. So as we go across, we start at very basic, slightly less basic, amphoteric, slightly acidic, very acidic. Okay, so basicity, so it goes from basic to acid. Basicity increases as you go down, and over this side, acidity does the same thing, or does the opposite. It decreases as you go down. So what you actually could say is that basicity is increasing as you go down here, and basicity is also increasing as you go down here. You could also say that acidity is decreasing as you go down here, and acidity is also decreasing as you go down here, because remember, it's a scale, so it's a scale between 2 points. So either way, if this here is basic and this is an acid, as we go down a group, it moves across that scale regardless. Alright, so why is this the case? Well, basically, metals like to give electrons, okay, and this is what gives them their basic nature. Now remember, so if we've got a lithium, he's got one as his thing, and he's got one lone electron in his outer shell there. For lithium, it's much easier for it to lose this electron, okay? Gives it a positive ion, and it's got its stable octet, so it's happy, or it's stable too. It's got its stable outer shell. So let's have a look at an example is involving barium. So if we've got barium oxide, right, because it doesn't mind existing like this. So when we put it with water, if you've got barium oxide, the reaction will occur to give you your hydroxide ions, which means it is happy to do this because it's lost its electrons, and it's done this to give it its stable outer shell. That's it. So stable outer shell leads to the oxide forming hydroxide ions. Okay. The converse is also true with non-metals. Okay, so over here we've got fluorine, and it needs one electron, so it will quite happily take that from water to leave just the hydrogen ion there, which has given up its electron. That's why it's got that positive charge. So this is how acidity relates to the opposition on the periodic table. So that's actually pretty cool. I find this kind of neat. This is, I think, the most interesting aspect of this whole video we're doing right now. So let's have a look at the trends. We've already discussed the trends, but let's have a look at why this is true. So we're bringing together the things we already know, and we're going to put them all together. All right, so sodium. It finds it much easier to lose an electron than lithium. Okay, so remember, basicity increases as we go down. Because it finds it easier to lose its electron, this means that sodium oxides are much more basic than lithium. Okay, that makes sense, doesn't it? Like, so because it's got that extra shell in here, it's not quite as attracted. It's easier for this to disappear than it is for this one, which will still happen, but it's just easier here, which means it's a stronger base. All right. Now, if we move across this way, and we said, starts super basic, less basic, amphoteric in the middle here. Somewhere, remember, we've cut out a bunch of the other ones. Transition metals have all disappeared. Amphoteric around here, and fairly acidic. All right. It is easier for lithium to form an ion than it is for boron. Okay, because to get the stable octet, lithium just has to lose 3. Lithium just has to lose 1. Boron has to lose 3, which means it's easier for lithium than it is for boron. So lithium is more acidic, more basic. Lithium is more basic than boron in its oxides. All right, now we said the opposite is true as well. So fluorine finds it much easier to gain an electron than chlorine does. What this means is that chlorine oxides are not as acidic as fluorine. Okay, so fluorine, it's just easier. It's easier to attract the electron because it's closer to the positive nucleus. So because it's closer to the positive nucleus, it's easier for fluorine to gain an electron, which means fluorine or fluorine oxides are more acidic. All right, so there's generalizations. What does this all mean? Basically, most metal oxides are basic. Most non-metal oxides are acidic. Some are neutral, not many, about 2 or 3. Some are amphoteric. You're looking at between 6 to 10. The trend is from basic to acidic across the periodic table. Basicity increases as you go down the periodic table. Acidity decreases as you go down the periodic table. All right, that's it. That was a long one. Hope you hung in there, and we'll see you in class.